Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on mathematics. Let's go ahead and get started with problem number 1. Problem number 1 says, how would the number 17,060 be written in scientific notation? Scientific notation is a way to express numbers as a coefficient between 1 and 10 multiplied by a power of 10. And this represents how many places the decimal point has been moved to simplify the number. To begin, we need to identify where to place the decimal point so that the number becomes a value between 1 and 10. For 17,060, we can place the decimal point here between 1 and 7. That gives us a number of 1.706. This is between 1 and 10, so it fits the criteria. Next, we want to determine the power of 10. Now, we're not given this explicitly, but essentially the decimal point is right here. And by creating the number 1.706, we have moved the decimal point 1, 2, 3, 4 places to the left. This means that the exponent on 10 is going to be positive since we moved the decimal point to the left, and it's specifically going to be positive 4. So 17,060 in scientific notation is 1.706 times 10 to the 4. Now I want to address why the coefficient is written as 1.706 instead of 1.7060. This distinction comes down to the concept of significant figures. So looking at the full number here, 17,060, this trailing zero is not significant because it is not part of a decimal number. When we're given this number, there is no decimal point. So when there's no decimal point, trailing zeros are not significant. So this number only has 4 significant figures, and we need to ensure that that's consistent when we write in scientific notation. This is why we do not include the 0, and the correct answer for problem 1 is B and not C. Beautiful. Let's move on to problem 2. Problem 2 says, how does the number of significant digits differ between 14,320,010 and 3.168000. Keep in mind that significant digits include all non-zero digits, all zeros that are between non-zero digits, and trailing zeros in any number with a decimal point. Let's look at our first number. This number is written without a decimal point. So that means that trailing zeros like this one right here are not significant. They just act as placeholders. However, the zeros in the middle of the number, these are always significant because they provide meaningful precision. So looking at this number as a whole, we have 1, 2, 3, 4, 5, 6, 7 significant digits. What about our second number? This number is written with a decimal point. So trailing zeros are significant because they indicate precision in the measurement. So this number has 1, 2, 3, 4, 5, 6, 7 significant digits as well. So we notice that both of these numbers have 7 significant digits, which means that the correct answer is answer choice C. Let's move on to problem 3. Problem 3 says, using the appropriate number of significant digits, what is the answer to the following math problem? Note, assume all numbers are the results of measurements. Here we have 3.060 times 4.10 plus 200. Let's begin with the multiplication. So the first thing we want to note is the number of significant digits in each factor. 3.060 has 4 significant digits because all non-zero digits and the final zero after the decimal point are significant. 4.10 has 3 significant digits because the trailing zero after the decimal is significant. Now, when you're multiplying or dividing numbers, the result must be rounded to the same number of significant digits as the factor with the fewest significant digits. Since 4.10 has 3 significant digits, our result will also be rounded to 3 significant digits. So when we perform this multiplication, we're going to get 12.546, and we want to round this to 3 significant digits, which gets us 12.5. Now we can move to the addition. So we have 12.5 plus 200. In addition and subtraction, the number of decimal places determines how we round the result. So specifically, the result must be rounded to match the smallest number of decimal places among the numbers being added or subtracted. Here, 12.5 has 1 decimal place. 200 is written without a decimal, so it has 0 decimal places. That means that the sum is going to be rounded to the nearest whole number. When we add these up, we get 212.5. Again, our decimal places for our final answer needs to be 0. So we're going to go ahead and round this number to 213, and that's our final answer. So the correct answer for problem 3 is answer choice B. Beautiful. Let's do 4. 4 says which of the following would be the most appropriate setup for estimating the value 3.6 multiplied by 4.85 for questions in which answer choices differ by a small margin. During lecture, we said that when we're estimating the product of 2 numbers, it's best to round one up while rounding the other down. This keeps our approximations logical and our final answer close to the actual value. Let's go ahead and work through these answer choices. In answer choice A, we're rounding 3.6 down to 3.5, and we're rounding 4.85 up to 5. This is good. This follows our rule. We are rounding one up and we're rounding the other down, and it's not by a huge margin. Let's take a look at answer choice B. In answer choice B, we're rounding down 3.6 to 3.5, and then we're also rounding down 4.85 to 4.5. This isn't the best technique to get a value that's close to the actual value. So B isn't our correct answer. Let's look at C. In C, we're rounding 3.6 up to 4, and then we're rounding 4.85 down to 4. Now, while this follows our round up one number, round down the other number, it's by a huge margin, especially when we compare it to answer choice A. So this is also not our correct answer. Finally, in answer choice D, we're rounding 3.6 up to 4, and then we're rounding 4.85 up to 5. So here we're rounding both numbers in the same direction. For multiplication, we really want to avoid this. So our best answer here is going to be answer choice A. Let's move on to problem 5. Problem 5 says the value of 200 raised to 0.25 is closest to blank. The key here is recognizing that the exponent 0.25 is equivalent to taking the fourth root of 200, because 0.25 is equivalent to 1 over 4. When you have 200 raised to 1 over 4, following our exponent rules, this is equivalent to taking the fourth root of 200. Now, let's recall what the fourth root means. That means we're looking for a number that, when raised to the power of 4, gives us a value close to 200. Now, since we're working without a calculator, we can use estimation by identifying nearby perfect fourth powers that bracket 200. So let's start with a few numbers we know and that are easy to calculate. Let's start with 2 raised to the fourth power. This is 2 times 2 times 2 times 2. This is equal to 16. What about 3 raised to the fourth power? This is 3 times 3 times 3 times 3. That's equal to 81. Now, this is still less than 200, but a lot closer than 16. Let's try 4 raised to the fourth power. This is 4 times 4 times 4 times 4. This gets us 256. Now, this value is larger than 200. This tells us that the fourth root of 200 lies somewhere between 3 and 4. And since 200 is closer to 256 than 81, we can say that it's approximately closest to 4, which means that the correct answer for problem 5 is A. Problem 6 says, if A and B are real numbers, which of the following equations is incorrect? Let's analyze each answer choice and figure out which equation is incorrect. Let's start with answer choice A. Here we have A cubed multiplied by B cubed, and this is equal to A times B, and that's all cubed. This statement is correct because of the product rule of exponents. When 2 bases A and B are raised to the same power and multiplied, you can just factor them under a single exponent. So answer choice A is correct, and we can go ahead and eliminate that answer choice. B says A to the 5th power divided by A to the 7th power is equal to A to the minus 2 power. Now, this statement is also correct because of the quotient rule of exponents. When you're dividing powers with the same base, you simply subtract the exponents. So this is A, 5 minus 7. This gives us A to the power of minus 2. So this equation is absolutely correct, and we can go ahead and eliminate it. Answer choice C says A raised to 0.5, and that's all raised to the power 4, plus A squared is equal to 2A squared. Let's focus on this first term. Here, we can simplify this using the power rule of exponents. This is simply going to be A raised to 0.5 multiplied by 4, and that's equal to A squared. So here, our equation is just A squared plus A squared is equal to 2A squared, and this is valid because you're simply adding 2 terms of A squared. So answer choice C is correct, and we can go ahead and eliminate it. Now we're left with answer choice D. This is incorrect because of the power rule of exponents. When you're raising a power to another power, you just multiply the exponents. So this should be equal to A to the 6th power, not A to the 9th power. So the only equation that's incorrect is answer choice D. That's the correct answer for problem 6. Let's move on to problem 7. Problem 7 says, how can the value of a natural log be converted to the value of a common log? Answer choice A says the natural log is divided by a constant. B says a constant is added to or subtracted from the natural log. C says the natural log is raised to an exponent. And D says the inverse of the natural log is taken. Now, from our lecture, we said if we want to convert a natural log to a common log, we use the following equation. Log x is equal to natural log x divided by 2.303. So what we see here is that the natural log is divided by a constant, which means that the correct answer is answer choice A. Problem 8 says, what is the minimum value of 2 cosine theta minus 1. To determine the minimum value of 2 cosine theta minus 1, we first need to understand the range of values that the cosine function can take. The cosine function oscillates between -1 and 1. This means that the smallest possible value of cosine theta is -1. We're going to use that value, we're going to plug it into this expression. So now we have 2 multiplied by -1 minus 1. This gets us -2 minus 1, and this is equal to -3. So the minimum value of 2 cosine theta minus 1 is -3, which is answer choice A. Let's move on to problem 9. 9 says, which of the following relationships is incorrect? Let's work through each of these answer choices, starting off with A. A says that the absolute value of the product of sine theta and cosine theta is less than the sum of their absolute values. This is absolutely correct. Since the product sine theta with cosine theta will always be less than or equal to either sine theta or cosine theta individually, their absolute sum will naturally be greater. We can demonstrate this with an example. Let's say that theta is equal to 45 degrees. Sine 45 degrees is equal to the square root of 2 divided by 2. And cosine 45 degrees is also equal to the square root of 2 divided by 2. The product of sine 45 with cosine 45, that's going to be equal to 1 over 2. On the other hand, the sum of their absolute values is going to equal the square root of 2, which is approximately 1.4. So we can clearly see that the sum of their absolute values is greater than the product. So this statement is absolutely correct. We can go ahead and eliminate answer choice A. B says sine theta divided by cosine theta is equal to tangent theta. Let's expand on sine theta and cosine theta and see if we can prove if it's equal to tangent theta or not. We said that sine theta is equal to opposite divided by hypotenuse, and that cosine theta is equal to adjacent divided by hypotenuse. When we're dividing the two, we notice that hypotenuse cancels out, and we're left with opposite divided by adjacent, and this is our definition for tangent theta. So this statement is absolutely correct, and we can go ahead and eliminate answer choice B. C is pretty simple. It says that tangent of 90 degrees is undefined, and this is absolutely correct. This is correct because at 90 degrees, sine 90 is equal to 1, cosine 90 is equal to 0, and we just said that sine theta divided by cosine theta is equal to tangent theta, but the division by 0 is undefined, so it makes sense to say that tangent of 90 degrees cannot be calculated. So C is also a correct statement, and we can go ahead and eliminate it. Answer choice D is what we're left with, and this tells us that sine theta is equal to sine 90 degrees minus theta. Now, let's try to figure this out by doing an example. Let's assume that theta is equal to 30 degrees. Sine 30 degrees is equal to 1/2. Sine 90 degrees minus theta, which is 30 degrees, that means we're doing sine 60 degrees. This is equal to the square root of 3 divided by 2. And so we notice that sine 30 degrees is not equal to sine 60 degrees, so this statement is incorrect. And since problem 9 is asking which of the following relationships is incorrect, our correct answer is going to be D. Let's move on to problem 10. 10 says, what is the approximate pH of a solution with a pKa of 3.6? Here we're given the concentration of the acid, 100 millimolar, and the concentration of the conjugate base, which is 0.1 molar. We're also given the formula to calculate pH. We're given the pKa, that's equal to 3.6. We're told that the concentration of the acid is equal to 100 millimolar. And we're told that the concentration of the conjugate base is equal to 0.1 molar. Now, before we go ahead and plug them into our equation, let's make sure that we adjust the units for the concentration so that they both have the same units. Here, I'm going to convert millimolar to molar so that our concentration for our acid has the same units as our concentration for the conjugate base. 100 millimolar is equal to 0.1 molar. Now we can go ahead and plug this in. The pH is equal to 3.6 plus the log of 0.1 molar divided by 0.1 molar. So here we have 0.1 divided by 0.1. That's just equal to 1. So we have 3.6 plus the log of 1. Now the log of 1 is equal to 0, so we have 3.6 plus 0. We can conclude that our pH is equal to our pKa, which is 3.6. That means that the correct answer for problem 10 is B. Problem 11 says, at what temperature do the Fahrenheit and Celsius scales give equal values? To solve this problem, we need to recall the formula that relates Fahrenheit to Celsius. That formula is that Fahrenheit is equal to 9/5 multiplied by Celsius plus 32. Now we're looking for the point where Fahrenheit equals Celsius. So we're going to replace this Fahrenheit term with a Celsius term to get that Celsius is equal to 9/5 multiplied by Celsius plus 32. Now we're going to solve this equation step by step. We're going to first subtract 9/5 Celsius from both sides. So now we have minus 4/5 Celsius is equal to 32. Now we're going to multiply both sides by minus 5/4. This gets us that Celsius is equal to minus 40. Now, this temperature doesn't match any of our answer choices because our answer choices are in Kelvin. So we need to go ahead and convert this temperature to Kelvin. So this is our Celsius temperature. To convert it to Kelvin, we simply need to add 273. This gets us 233 Kelvin, which matches answer choice B. So 11 is B. 12 says in a certain rigid container, pressure and temperature are directly proportional. If the pressure is changed from 540 torr to 180 torr via a temperature change, by what factor has the temperature changed? A direct proportionality means that as one variable changes, the other changes by the same factor. For this situation, if pressure decreases, temperature must also decrease by the same ratio. To solve this, we examine the ratio of the initial pressure to the final pressure. The factor by which pressure changes can be calculated as P2 over P1. So this is 180 torr divided by 540 torrs, and this gives us 1/3. Since pressure and temperature are directly proportional, the temperature will also change by the same factor. So that means the temperature decreases to 1/3 of its original value. The correct answer to problem 12 is answer choice D. Beautiful. Problem 13 says, a 150-pound adult must be given a drug that is dosed at 1.5 milligrams drug per kilogram body mass. Approximately how many milligrams of the drug should be administered per dose? Note that 1 pound is equal to 4.45 newtons. Because grams are a unit of mass and pounds are a unit of force, we first have to convert pounds to newtons and then divide by the acceleration due to gravity to find kilograms. We're told that this adult is 150 pounds. We can convert this to newtons because we know 1 pound is equal to 4.45 newtons. Pounds cancel out. We're left with units of newton. Here I'm going to approximate this to 4, and 150 multiplied by 4 is equal to 600. Then I'm going to take 600 newtons. I'm going to divide this by the acceleration due to gravity. This is 9.8 meters per second squared. Now I'm going to expand newtons. 1 newton is equal to 1 kilogram times meter per second squared. So I'm going to write it in that form. And I want to do this because it becomes clear what units cancel out and what unit our final answer is going to have. Meters per second squared cancel out. Our answer is going to have units of kilograms. 600 divided by 9.8, I'm going to approximate 9.8 to 10. 600 divided by 10, that's easy. That's equal to 60. Now that I have the mass of the patient, I can determine the dose. We're going to take 60 kilograms. We're going to multiply this by our conversion here. For 1 kilogram of body mass, we need 1.5 milligrams of the drug. Here, kilograms cancel out. Our final answer is going to have units of milligrams. 60 times 1.5 is equal to 90. This is closest to answer choice C. So the correct answer for 13 is C. Let's move on to problem 14. This problem says the rate of reaction is calculated as a change in concentration per time. What are the units of the rate constant K in a reaction that is second order overall with respect to one species? This problem wants us to analyze the rate law for a reaction that is second order overall with respect to one species. And we're given the general rate law for such a reaction. Rate is equal to the rate constant multiplied by the concentration of the species squared. Now here, the rate of reaction, this is going to be expressed as a change in concentration over time. So it's going to have units of molarity per second. For this concentration term right here, concentration of the species, this is going to be expressed in molarity as well. And since the term is squared, this is going to be molarity squared. What we have here then is molarity per second is equal to the rate constant multiplied by molarity squared. We can go ahead and divide both sides by molarity squared, and we get that K, the rate constant, is equal to 1 over molarity times second. Now M is shorthand for molarity, which is equal to moles per liter. So let's go ahead and replace that term with moles per liter. And don't forget, this is multiplied by seconds. We can re-express this as liters divided by mole times second. And this matches answer choice C. So the correct answer for problem 14 is answer choice C. Now we can move into our last and final problem. Problem 15 says, one group of people requires a base level of 900 calories per day plus an additional 12 calories per kilogram of body mass per day. A second group requires a base level of 500 calories per day plus 15 calories per kilogram of body mass per day. At what mass does the first group and the second group have the same caloric needs? From this information, we can actually construct two equations. So for the first group, the amount of calories they need is their baseline of 900 calories per day plus an additional 12 calories per kilogram of body mass. For the second group, they have a base level of 500 calories plus 15 calories per kilogram of body mass. Now that we have these two equations and they both equal the number of calories, we can set them equal to each other and solve for m. This is going to tell us at what mass does the first group and the second group have the same caloric needs. So 900 plus 12m is equal to 500 plus 15m. We're going to subtract 12m from both sides. This way, we get rid of this term on the left side. And then we're going to subtract 500 from both sides as well. This allows us to get rid of that term right there. So now we have 400 is equal to 3m. Then we divide both sides by 3, and we get that m is approximately 133 kilograms. So the correct answer for problem 15 is C. And with that, we've completed our practice problem set. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.